Alright, engineering students, this is going to be the second video for this week. This is going to be a pretty short one. Again, I apologize for this one coming out late. I'm going to just go through one more example of how the equilibrium equations work, and that'll be it. We'll just do one, just one. That'll be enough for us. Let's look at a situation where we have something that has forces that aren't perfectly perpendicular or horizontal. Very important situation. We're going to put a little hinge right here. Okay, and what else will we do? Let's see. Let's put a simple support right here. So it's just resting on that one, but it's hinged at this one. I don't know what's a good analogy for this? This could be like one of those bridges where boats go underneath, and maybe it kind of goes up and down like that to permit the boats passing through here. That's a very, very shallow canal. Whatever the situation, that's what we're talking about. And I am going to mix it up a little by, let's see, I'll put I don't know, let's say maybe there's a car right here. How much does a car weigh? A car is about, I don't know, at least 20,000 newtons. That's a fairly light car actually. But also, maybe there's like a cable system. I realize I'm not strictly doing free body diagrams right now because I'm drawing other stuff. I haven't isolated this from the universe. But let's say that there's like a pulley system with a cable that attaches, and that's what pulls it up when it's time for the boats to go through. Okay, there's our little tugboat. I'm having way too much fun here. You like that? This is definitely not a free body diagram right now. So let's make it a free body diagram. That just paints the picture for you. We're going to get rid of all this extra stuff because the first rule of a free body diagram is that you get rid of the rest of the universe. Okay, so we've done that. Okay, so we're going to show the external forces. I've got a car, a single car, 20,000 newtons weight, and then let's put as I said, a cable right here, and we're going to have this cable at a 30-degree angle with a tension force of, let's make it easy, 10,000 newtons. By the way, I could have written those as 20, which prefix? Kilonewtons, little k, and this would be 10 kilonewtons. Same thing. Just means you have to write fewer zeros. Okay, what else I need to do? I got to show next. So those are the applied forces. And by the way, notice here, I'm making a little shortcut, I guess. I'm ignoring the self-weight. This was mentioned in the textbook. I'm not sure if I direct you to that part or not. I don't remember, but in the textbook it does say that the author says usually we do ignore the self-weight. I don't know if that's true or not. Depends what your level of analysis is. Let's say for this one we ignore the self-weight of the bridge because we say that the external forces are far more significant. All right, so let me just write that down. We're ignoring self-weight. And I'm going to put a question mark because it is some judgment as to whether you do that or don't do that in each analysis. But what I do need to show, marching through the list of things, is the possible reaction forces. Let's actually do this, by the way. Let's call this location 1. Maybe I'll call this location 2. I'm going to call this location 3 and this location 4. I probably should have done that on the other examples if I'd thought more clearly. This just helps us keep track of what we're talking about. So there is going to be a single unknown vertical reaction force here. I'll call this R1Y because it happens at location 1 and it's vertical. For a pin joint, we have one unknown vertical. I'll call this R4Y because it's at location 4. And then there is another R4X, okay? A pin joint keeps things from sliding left-right, keeps things from sliding up and down, but does not provide any moment resistance. We actually haven't done a fixed situation yet. I might leave that one maybe for next week. Alright, so those are our reaction forces. There's no friction here, there's no, yeah, I guess that's the only other thing in our list of 4 things. We've always done self-weights, applied forces, reaction, ground, normal forces, and friction. So I think we've accounted for all of it. So all we have left to do now is run through the equilibrium equations and solve these missing reaction forces. Okay. We know what those are. Actually, let me do something too. Good habits. Let's just absolutely define our positive directions. We can't do that too often, okay? Always do that as much as you can. The horizontal forces, with this as the positive direction, will sum to 0. The vertical forces, make sure you put those subscripts in, will sum to 0, with up being positive. And we will sum the moments, with that being the positive direction. And we get to pick. I've only been doing the leftmost point up to this point, which would be, in this example, 1, location 1, okay, right here. But let's try something else. Let's see. Why don't we do location 4? Okay, this one here. I just want to show you that it can be done around any location. So the moments around location 4. Okay, now before I get into the details of those, I actually want to do one thing. This is something that I haven't had to do in any of our previous examples. And what that is to break down the angled force right here into its horizontal and vertical components. And you have to do this because that 10 kilonewton force is not lined up vertically or horizontally. Now we've been doing this for a few months already, so this is like an old skill at this point. It's supposed to be an old skill at least. So here's how we do it. I'm going to work in red. I know it's kind of an alarming color, but so there is a horizontal component force, and there is a, oops, let me redo that. I'm going to make that more accurate. There is a vertical component force. Okay, we're asking how horizontal-ish is that 10 kilonewton force, and how vertical-ish is it? And the answer to those, if you've forgotten how to do this, then you probably need to go back and watch some other videos. But remember, like, these are all right-angled triangles. And by the way, it doesn't matter if you show the vertical force here. That is acceptable, but it's a little misleading because it looks like it's not originating from location 3. That's why I'm drawing this as a rectangle and not just a right-angled triangle. It's actually 2 right-angled triangles. So the shortcut, remember, is that this is 10,000 times cosine of 30. That is the magnitude of that component. And I have my calculator right here. You can hear the click and clack as I get it ready. Over here we got 10,000 sine 30 degrees. And so making sure that I am in degrees mode, I work that out. That is, I'm going to say 8,660 newtons. And on the other side, those of you who know trig should know what this is before I press the enter button, 5,000 exactly. The reason for that is that sine of 30 degrees is equal to 1/2. Don't ever forget that, folks. Cosine of 30 degrees is always equal to root 3 on 2. That's root 3 on 2 times 10,000 gave us the 8,660. Don't ever forget them. Okay, so now I think we're actually ready to sum up all the forces horizontally, vertically, as well as the moments. Let's do it. For the horizontal forces, we have recording. Yep. Miss Isaac's trying to bang on my door, but I'm recording. Okay, horizontal forces are, let's see, 8,660. That's horizontal in the positive direction. And then we have negative R4x. Okay, that's all that's happening horizontally. 8,660 in the positive, which is to the right, and negative R4x because it's to the left. And that's it, we have 2. Now this is the first example where we've had 2 horizontal forces to account for. So this is new. Vertically, things are kind of predictable compared to the other examples. We have R1y is positive upwards. Let's do the unknowns. R4y is positive upwards. We have a negative 20,000. I'm really wishing I was working in kilonewtons actually at this point. All those zeros get in the way. And then we have a positive 5,000. Okay, that's this right here. Everything looks to be accounted for. I'm double checking. Okay, now the moments. Moments around location 4. And by the way, I chose location 4 because there are 2 forces shooting straight through it. So that's a great way to eliminate moments from the get-go. We have, oh, you know what I forgot to do? I forgot to give our scale. I'm sorry. Let's say that each square is just 1 meter. Keep it real simple. I did intentionally match to the squares when I drew it. Okay, so the moment. So first of all, R1y is force times distance. I got to count squares here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What an awkward number. Times 11, and this is going to be negative because it is trying to spin this way around that hinge point that we chose. Whether it is truly a hinge or not, whether this thing actually moves or not, remember that is irrelevant. We're just summing the moments around any arbitrary location. Okay, the next one, working our way along, we got a positive 20,000 times 1, 2, 3, 4, 5, 6, 7, 8 times 8 meters. That's coming from this one going this way. What else? We have minus 5,000 times 1, 2, 3, 4. And that is the end of it. This 8,660 doesn't cause a moment around point 4 because it is also shooting straight through that hinge, and these ones don't for the same reason. Okay, so that's it. Now we work on it. We got 3 unknowns. Okay, we have R1y, R4y, R4x. And we have 3 equations, fx, fy, m4. And that, remember, is the magic situation. The same number of simultaneous equations, or the same number of a system of equations as what unknowns you're trying to uncover. Sorry, I said that very badly. So we can do this. Let's work it out. First one's pretty easy. We take the fx equation and we simply rearrange it. We subtract r4x. We add r4x to put it on the left-hand side, and that just answers itself. There it is, r4x. We found it. 8,660 newtons, 8.66 kilonewtons. Done. And now that kind of removes that out of the way. Now we have, you could say we have two equations left with two unknowns. So again, very, very solvable. Let me rearrange the fy equation. I'll clean that up a little bit. We have r1y plus r4y. Negative 20,000 plus 5,000 gives us negative 15. We add the negative 15 to put it on the other side, and we get that. Okay, that is the simplified fy equation. I'm just getting that directly from this line. Alright, and then we do the moment one. Let's see, I will add 11 times r1y to both sides. And then I will combine the 20,000 times the 8. What is that, 160,000? I guess it is. 160,000, then I got a minus, yes, I'm doing this on a calculator, minus 20,000 gives us 140,000 positive. Okay, that's just me rearranging this equation. Alright, I think everything's in order. I think we're doing well. So now we're going to do our little trick. We're going to say, you know what, we could multiply everything here by 11. That would level the playing field. Let me move down a little bit. So that would give us what? 11 r1y plus 11 r4y equals 165,000. All right, and then we can, let's see, we are going to be subtracting those two equations from each other. It doesn't matter which one you subtract from the other, by the way, in case you're wondering. I'm going to do that equation minus this equation. So 11 r1y minus 11 r1y leaves us with a cancellation, which is that's why we times by 11. The 0 minus 11 r4y leaves us with negative 11 r4y. And 140,000 minus 165 leaves us with negative 25,000. Again, I'm wishing I had recorded this in kilonewtons from the outset. Okay, we are going to divide both sides by negative 11. So let's do that. And we get r4y is a very messy but positive 2,000, and I'm gonna do three significant figures. 2,270. All right, that is r4y. And remember, the fact that I got a positive answer means that my initial guess as to the direction of r4y is correct, was correct. That's what the positive answer means to these equations. Let's see, maybe I'll get a, no, I won't, that's fine. Oh, I just noticed something I did that was wrong. I'm sorry. Let me fix something. I was not paying enough attention. We said here it was r4x that was 8660. If you were wondering why I wrote it over there for r1y, it's because I was wrong. I should have written it right there. That was just a mistake. Okay, now we go back, and we still need to find out what r1y is. So what can we do? Ooh, you know what? r1y is actually pretty easy. We can use this line right here. We have a simple situation. If 11 r1y equals 140,000, well, guess what? r1y is 140,000 divided by 11. So we get 12,730. Where's that? Okay. 12,730 newtons. So, you know, if I had been paying more attention, firstly, I would have put R4X on the correct location. I should have seen this line straight away. I should have seen, you know what, wow, there's an equation there with one unknown. That can be solved in and of itself without the need for adding and subtracting. So I should have done that next. And then from there, I could have simply substituted the answer for R1Y. I should have substituted that into this equation before multiplying by 11. I didn't need to do the times 11 subtraction thing. I could have just put that in here, and then I would have instantly subtracted across and gotten an answer for R4Y. I would have gotten the same answer of 2,270, but it would have been slightly clearer. All right, now just to take a step back, obviously you can replay this video if you need to understand this again. You can ask me at lunchtime, things like that. But just take a step back and look at what's happening here. What this is all saying is that with this car right where it is and this cable pulling where the tension is right now, there is a whole lot of reaction force required over at location 1. Okay, that's where the bridge is really experiencing, you know, some action, some reaction, I guess. Interestingly, over on R4Y, when you're talking bridges, 2,000 newtons roughly that it's experiencing, that is nothing. That is negligible, okay? So it's like the cable's tension and the car's load are actually kind of almost canceling a little bit to essentially create a very gentle reaction force over there. And then interestingly, the pin joint had to actually do some work horizontally because that cable is pulling sideways as well as upwards. That horizontal reaction force actually rose up and was required. Otherwise, this bridge, let's say this bridge had been on like 2 rollers at both ends or 2 simple supports at both ends, the bridge would have actually been like sliding across in the right-hand direction under the action of the cable pulling on it. Okay, so the pin joint is doing an important job here. All right, that's my commentary. That is also the end of this video. I think that summarizes for you. It takes just a little deeper than the first video this week. How do you handle forces that don't come at you purely horizontal, purely vertical? Well, the answer is, yeah, you actually have to use all 3 equations for real. And you've got to break down into components using trigonometry, using the stuff we'd already spoken about. So, thank you for your patience. Again, I apologize this video came out a little late, but I think we got there usefully in the end. Have a great Thanksgiving, and we'll see you guys on the other side with, next week, when you come back, we'll have the videos of your clients and which design they selected, and I'll give you more information about it. See you later.